Hello everyone, my name is Gabriele Pignalberi and today I will talk about predicting a known viral host using dynamic positive-unlabeled learning. The goal of our project is that of network reconstruction, or in other words, to infer which links are the most likely missing in a network where only part of the associations are known. However, in real-world network reconstruction, we almost never have confirmed negative associations, and the associations that we do observe are usually only a biased subset of the real existing ones. All of this makes it harder for our models to learn patterns that are actually representative of the actual ground truth of the full network and that are not instead biased towards documented associations alone. These issues are especially important in mammal-virus associations networks, where sampling varies dramatically across both mammal species and viral families, and poses a very critical problem for exact knowledge about geographic and taxonomic distribution of mammalian hosts of important viruses, with severe consequences to our preparedness to future zoonotic events and thus potential novel pandemics. To address these problems, we introduce here the Dynamic Positive-Unlabeled framework, or DPU, which is a novel semi-supervised approach designed to predict missing associations in networks that report only a biased subset of all the truly existing links. In particular, we applied DPU learning to the global network of mammal-virus associations, where reported associations between mammal species and viral families represent the capabilities of mammal species to be infected by viruses belonging to the viral family considered. The core idea of DPU learning is that the probability of observing association X, given all the labels of other associations in the dataset at a given time, can be decomposed as the probability of association X to be fully existent and the probability of association X to be observed given it exists. Thus, the core intuition of the DPU approach is not that to train just one single model, but to actually train simultaneously two distant and different models. A classifier, which reproduces the likelihood of an association to be existent given the labels of the data in the dataset, and a propensity score model, which reproduces the propensity scores for associations that are the likelihood of association to be observed given they exist and given all the observed association in the dataset at a given time. Both the models are needed to predict missing links in an accurate way. In particular, the DPU training is based on two different phases. The first phase, we train the Bayesian DPU model for estimating the joint posterior of propensity scores for all association in the dataset, and in particular, this is based on a twin hierarchical model based on mammalian taxonomy and other proxies of research efforts for accurate inference of propensity scores for associations. And thus, using this joint probability, we sample propensity scores configuration in order to train an ensemble of models based on different DPU risks. In particular, DPU risk is defined using the propensity scores, and it is based on the idea that labeled associations are considered as positive associations, and negative associations are labeled associations are considered as negative associations. But there is also a term which corrects for uneven sampling bias and for the fact that unlabeled associations are not actually cannot be actually epistemically considered as truly non-existent associations. The classifier model is based on a graph neural network model which uses mammalian phylogeography, mammalian traits, genomic characteristics of the virus, and observed patterns of mammal-virus associations in order to extract another representations both for mammal species and viral families nodes, and using this final node representation in order to predict likely missing mammal-virus association. Finally, the results shows that our TPU model is actually able to reliably recover new empirically confirmed associations, that is, associations that were unlabeled at the time of the training that have been later discovered as truly existent, but also to recover the truly existent links, unlabeled links in datasets, synthetic datasets that we created. This provides that the model achieved high validation performances, and it can be used to yield unbiased and accurate probabilistic estimates of missing links.